I hate every time I have to say it. Just like you could have a question like this on the calculator part of the exam or the non-calculator part of the exam, and we've all been in that situation where you're taking a test. You have absolutely no idea how to solve the problem by hand. You do know how to do it on the calculator, so you get it right because you're allowed to use your calculator, but there's that moment of like, what if this were on the non-calculator part, what would I do? All right, so we always have to be prepared for the worst and hope for the best. All right, so this is the general process, but it's not really anything that you need to memorize because it's just thinking about the characteristics of a graph. You know, what are some things that come into play when you're graphing a function? You have things like asymptotes, you have intercepts, you have symmetry, whether it's an odd or an even function would define that or determine that. Any kind of discontinuities, and then you get into the calculus stuff. So then we start talking about increasing, decreasing, relative extrema, absolute extrema, and then points of inflection and concavity. All right, so it's basically a whole lot of pre-calc right here, and then calc 6 and 7. Right, and that's generally the theme for a lot of the stuff that we do. It's like the calculus usually finds itself in one or two steps in a problem, but it's not overwhelming in the way that the solution works out. It's the pre-calc that can be overwhelming if a problem's difficult. All right, so that's what you're going to see here, basically. All right, so the first example, and it's already a red flag because example 1 has its own page. You know, so you know you're in for a ride. All right, so domain and range. Well, we'll just focus on domain, really. It's a polynomial function, so it's negative infinity to infinity. The range would be restricted. I don't know what the range is. In fact, we would get the range once we do all the calculus stuff, because we're talking about a quartic function. So quartic functions typically have a look along this lines or something like that. All right, so M shape, W shape, you know, any kind of variation of that. Because I mean, I've seen some funky ones where it's like, it's barely qualifying as a quartic function. So you see something like, you know, it goes down like this, and then it's like that.
Are those asymptotes at the end, or are they going out?
They're infinite, going out.
So then wouldn't the range be the same as the domain?
Well, you have a turning point, a defined turning point on the low end.
Oh.
On the high end, it would be infinite, but on the low end, it would stop somewhere. All right, but that purple one, it's like, wait, that's quartic? Yeah, because there's ever so slightly a little relative minimum there. It's just, it's not always visible to the naked eye. So, you know, it barely, like I said, barely qualifies as a quartic function, but it is one. All right, so, you know, we got to be on the lookout for anything. So that's why I say domain and where possible range, because sometimes you have to do the calculus in order to find the range. X and Y intercepts. Oh, and just going back to range for a second. If you were to do it without calculus, what you would have to do is actually find the inverse of the given function and then find the domain of that. If it were something like f of x equals just x to the fourth, no problem. But because it's that, I mean, yeah, you could switch x with y, but best of luck to you in solving for y, right? It's not going to happen. So this one is a situation where I think you wouldn't have to think about it too long before you realize that calculus would have to be involved. All right, so x and y and or y intercepts. The y-intercept is usually pretty easy to find when you're dealing with a polynomial function, because y-intercept you get just by plugging in 0 for x and seeing what you get. In this case, if you plug in a 0 for x, it goes to 0, so that's great. So I'll state my y-intercept. So I don't have to do any work for that. So 0. All right, if the y-intercept is 0, that's the origin. So that's telling us, you don't have to write it down yet, but it's telling us that the x-intercept for this function is also going to be at the origin, or one of the x-intercepts. We could have up to 4 of them, so that's fun. So x-intercepts, we would get, because it's polynomial, degree 4, we would get that by using the rational root theorem, all right? But we do have a GCF, so we could pull that out, all right? So we can at least make it a degree 3, all right? So f of x can also be thought of as x times x to the third minus 12x squared plus 48x minus 64. All right, so we know that we can take each of these parts and set them equal to 0. All right, so each part we would set equal to 0. All right, and that's telling us that we're going to use rational root theorem on this cubic function now. So that's your synthetic division with the p and q stuff. So let's go through that real quick. So coefficients of the cubic function: 1, negative 12, 48, negative 64. Bring down the 1. Some nice trial and error about to happen. Okay. When you're thinking about the possibilities for the outside, it's always the ratio of the factors of the constant term to the leading coefficient. All right. So the p-value, you don't have to list them out. The p-values are all the factors of negative 64. The q-values are all the factors of the leading coefficient, but the leading coefficient is 1. So you're just going to take the factors of this and divide it by a positive or negative 1. So it's not going to have an impact. So in this case, I could just look at factors of negative 64. All right. So I'd start with 1. That didn't work. If the leading coefficient were something other than 1, you'd have some fractions in there. That would be fun. Bless you. That would be my reaction too. I'm allergic to those problems. Let's see, 51. No, that's not going to happen either. So the 1s are out. All right, 2.
Are we just going in order of numbers?
All factors of 64.
Oh, okay.
So, but we are going in order
Oh,
of all those factors.
We didn't write it.
Right. So 20, 28. Nah. All right, so we'll try negative. Negative 2. This will be negative 14. That's going to be 28. Oof. All right, so I don't even know. Oh, the eraser's working. It's so temperamental. Sometimes it works, sometimes it doesn't. I got to learn like why it worked that time, but when I make like an obnoxious error that I need the internet to not see, like I can never get the eraser to work. Whatever. Maybe it just knows that I'm doing trial and error, like key phrases. So I think I tried negative 2. So let's try 3. Oh, 3 is not a factor. 4. 4 works. Yay. All right, so, yeah, I mean, we got there. Just glad it wasn't negative 64 that was the first one that worked, you know, it's kind of a win. All right, so, we're looking at x squared minus 8x plus 16. Factors are x minus 4 squared. All right, so if I set that equal to 0 and solve, we're going to get x equals 4 again. So double root for that, including the 4 that works, it's actually a triple root. All right, so our x-intercepts are 0, and I'm going to write 4 multiplicity 3. All right, multiplicity of 3 is, for me it's important because I like to identify that because it gives me a sense of what the graph is going to look like. All right, when you're talking about multiplicity, it's a very quick topic in pre-calc if it's even discussed. Depending on what the multiplicity is, so the power of a factor, it gives you a sense of the shape around the x-intercept. Right? So if it were a multiplicity of 2, then the graph behaves like a parabola at the x-intercept. So the x-intercept itself will be the turning point of that parabolic component. Right? If it's multiplicity of 3, it behaves like a cubic function around the x-intercept. Right? So I actually have a good sense of what this graph is going to look like now. If I had to draw a rough sketch, and oftentimes that's all you have to do, just by knowing that information, I would plot 0, 4. It's a positive quartic function, so it's going to go to positive infinity. So it's going to go directly through 0 because it's a multiplicity of 1. So it behaves like a line around that x-intercept. And then when it comes back up, somewhere over here, it's going to behave like a cubic. So it's going to look something like that. All right. So really the inflection point, and so multiplicity of 3 tells you that the inflection point of that cubic is going to happen on the x-axis. All right. So you get a lot of good information, a lot of pre-calc kind of informing the calculus of it. We do have to go through the motions calculus-wise, but we already have a sense of what the answer is. And if it's a multiple choice question, if it's asking you where is the inflection point in something like this, if you know it's in a multiplicity of 3, then you know that the inflection point is going to happen at one of the x-intercepts. Right? So that's pretty cool realization. And it allows you to get an answer quickly without having to take derivatives and making sign charts. All right, so pretty useful stuff there. Ultimately, I was just looking for x-intercepts, so if that's all you got out of it, that's good too. All right. So points of discontinuity are relevant. Symmetry, we kind of addressed it because if we have a sense of what the shape is, then, you know, like intuitively we know whether it's an even function or an odd function, because if it's not going to be symmetric around the y-axis, it's not going to be odd. If it's not symmetric through the origin, it's not going to be, sorry, I got that backwards. If it's not symmetric about the y-axis, it's not going to be even. If it's not symmetric about the origin, it's not going to be odd. All right. And based on this rough sketch, it doesn't have any symmetry through axes or the origin or whatever. Asymptotes are relevant. Points of discontinuity are relevant. So we can get into the calculus of it. Generally, I mean, even though we have information about the x and y intercepts, you don't want to start the sketch until you have a sense of extrema, because I don't know if that's going to impact scale. I don't want to start plotting points and then find out that I had to go by 2s or 3s or 10s or whatever. All right, so sit tight on the graph until you get some more information, particularly the extrema. All right. The good news is because it's a cubic quartic function to start, the derivative is going to be very easy. So f prime of x. So 4x cubed minus 36 x squared plus 96x minus 64. All right, so for extrema, got to set it equal to 0 and set it equal to 1 over 0 where relevant. It's not relevant here because it's polynomial, so just set it equal to 0. Looks like I have a GCF. All right, so I have to solve this now. One, -9, 24, -16. Now, it's going to end up being kind of nice, but you can't make that assumption. So oftentimes what happens is you'll have really, I mean, I don't think it's a contradiction always, but when you find a point of inflection, oftentimes that'll also give you 0 for the first derivative. So critical values of points of inflection often go hand in hand. So if I set my first derivative equal to 0 and solve, and I get like x equals 2, so, pretty often when I set my second derivative equal to 0, I'll get the same answer. All right? Because I recognize that it was multiplicity of 3, therefore giving me a point of inflection at x equals 4, I just took a stab at it to see if potentially we were looking at, you know, a case where that would happen. So I tried the 4, it worked, awesome. All right, now I have something that's factorable. So x squared minus 5x plus 4. So x minus 4x minus 1 equals 0. So we get x equals 4 and 1. All right, so my critical values. X equals 4, multiplicity 2, and x equals 1. All right. So what I learned from this, it's pretty strange, but it tends to happen. The x-intercepts were, well, one of them was 4 with a multiplicity of 3. 3 indicating a cubic function around that point. All right? Derivative of a cubic function is quadratic. All right? So the derivative function has a root that's 4 multiplicity of 2. For polynomial functions, that's something that happens pretty frequently. Not always, but very frequently. All right? So if you observe multiplicity, oftentimes you can get a sense of what your critical values are going to be just from that piece of information. All right? So I have that. And also, if I take the second derivative, it was 4 multiplicity of 3. Now it's 4 multiplicity of 2. Perhaps it'll be 4 multiplicity 1. All right, so let's take a look at our second derivative and see if that comes into play.
Wouldn't having a multiplicity indicate to you relative extrema or inflection points, because you know if they just touch the x-axis?
But that's what the derivative graph would look like at that point. Right? So if I were evaluating just that function, then I would know. But because it's pointing back to the original function, it gets a little foggy. So my second derivative would be 12x squared minus 72x plus 96. Set it equal to 0. Go to GCF again. GCF of 12, so x squared minus 6x plus 8. So x minus 4x minus 2. So my possible points of inflection. Pospoi. I'm not going to write 4 multiplicity of 1 because that just seems silly, but I mean, I guess it's not that silly, but it is multiplicity of 1. There's only one. And also 2. All right? So the x-intercept was 4 multiplicity of 3. Critical value 4 multiplicity of 2. Possible point of inflection 4 multiplicity of 1. All right? So that 4 seems to be rearing its ugly head over and over again. It's not really ugly. It's a good-looking number.
Stunning.
Yeah, it's very attractive. Actually, what do they call it? I should know this because I'm a math teacher, but the numbers that are the product and the sum of the same number? Square numbers?
Yeah.
I think. 4 is like 2 plus 2 is 4, but 2 times 2 is 4. There's certain numbers that satisfy that.
Yeah.
So it actually is a really beautiful number. So we need a sign chart to get a sense, or at least verify what this graph is going to look like. And so that's good because, again, we already have a sense. If you know what cubic functions, quartic functions, polynomial functions look like, this is kind of like just confirming what you already knew. But this process will flesh out less familiar functions. You know, like if you're taking a log of a quadratic function. You know, so, but when you're making the sign chart, if you really think about it, the important values would be, and we talked about this over the last few days, critical values, possible points of inflection, and any discontinuities. Well, the 4 came up over and over again, so it's not unique. Really, I'm just looking at 1, 4, and 2 in my sign chart.
It's just called a sum product number.
Oh.
Yeah, that's horrible.
We should make it by name.
Yeah, well, we'll call it a can number. Yeah, because I clearly discovered the concept.
Square sum. It's just like 2
No, I was thinking because geometrically that wouldn't work, right? The sum and product. No, actually, maybe it would. I got to look into this. I haven't invented something in a while. All right, so 1, 2, and 4 are important values. We know it's everywhere continuous, so that kind of sucks. For these kind of problems, you're sort of looking forward to discontinuities because they give you kind of a leg up in developing your sign chart because your discontinuities have to be in there. I mean, you're not looking forward to them now, I guess, but down the line you will. All right, and so this is one of those situations where the need for a sign chart gets called into question, right? And you'll see this. I mean, when we do the word problems related to this stuff, you're like, do I really need to create a sign chart because it's obvious by the function that it's a maximum versus a minimum. You know, it's a parabola that opens upwards, so it's the minimum. Why do I have to make a sign chart? Because the College Board says you need to make a sign chart. I mean, again, I hate saying it, but that's the reality of it. And this is one of those situations, like you already know, if you have a sense of polynomial functions, what the shape is. So you know where it's increasing, decreasing, concave down, concave up. So in reality, you're not really looking at any of these numbers to plug them in. You're really getting a feel from your graph of where the function is increasing, decreasing, and what type of concavity it has in order to fill out the sign chart, just to satisfy the need for somebody in the College Board who is overly obsessed with sign charts. All right. So again, a quartic function looks something like W-shaped, but we know it has a cubic feel to it at some point, so it's going to look something like this. So you could build off of that idea. All right. So, but you also have to make some kind of assumptions here. And the big assumption would be that this is the inflection point.
Would that be wrong?
It would not be wrong. Based on the multiplicity, we knew already it was an inflection point. All right? So it's just a question of what's going on around it. It's concave down and concave followed by concave up, just based on the fact that it's a positive quartic function. It has to take that shape. If it were a negative quartic function, so the kind that would go to negative infinity, then it would be the reverse. All right? But because it's going to positive infinity for y, or at least as you go out to negative positive infinity in terms of x, it has to take on this shape. There's no other way it can happen. All right? And still be quartic. So I know that to the left of 4, it's going to be concave down. To the right, it's going to be concave up. But there is some other transition point happening where it goes from concave up to concave down. So we're looking at another point of inflection somewhere over here. And we also have a relative minimum definitely here. We have 3 values to play with here. The smallest of them has to be the relative min. And this is all assuming that you don't want to just plug in numbers and figure it out. All right, so the smallest of them has to be the relative min. The next 2 are the points of inflection. All right, I know it's a relative min because going into it, well, I know it's relative min because it's the bottom. You know, you look at it, it's the lowest points. But calculus explanation would include the idea of increasing and decreasing. So decreasing first, then increasing from there on out. So decreasing going into 1, increasing everywhere else. Concave up until it gets to the first inflection point, which would be at 2. So that's a positive second derivative. So concave up, then concave down. There needs to be a change in concavity around your inflection points, otherwise it's not an inflection point. So a continuous point at 2 and 4 with a change in concavity. So if I know it's concave up, and I have 2, starting off a concave up, and there's 2 inflection points, it has to go down then up again, because there has to be a change. And that plays out in the graph. All right, so concave up on this interval, then it's bowed downward, then it's bowed back upwards. All right. The alternative to that, I mean, see these 2 bad boys right now? Well, pick a number from negative infinity to 1, plug it in there, and there. Pick a number between 1 and 2, plug it in there and there. Okay, we don't want to do that. All right, we want, well, we'll settle for having to do that. It's to be avoided if possible. So getting a sense of different types of polynomial functions, and actually different functions in general, is very important. All right, we're going to do an activity, not tomorrow. Today's Tuesday, right? So Thursday or Friday, where you're going to practice just identifying different types of functions based on their graphs. All right? So really, the whole thing is just naming the function. Right? If you can name the function, then you're already ahead of the game. Right? So then we have to create the graph. All right? And I'm going to show you a little trick. Well, I'm going to show you again a little trick because it should have been something in pre-calc, but it's a time saver when it comes to evaluating a function. Right? So if you got to a point where you're like, I don't know what this function looks like, I got to plug the numbers in, this sucks, I'm not going to finish the test, you might consider using this technique. The reason why we're going to do it here is because, yeah, I have the x values of my extreme values. I mean, I know that the 4 is a point of inflection and also an x-intercept, so I could plot that on the graph. The 0 is fine. But the 1 and, the 1 and the 2, I don't know where they are in terms of y. So I got to figure out those values. So I need my relative min, x equals 1, and my point of inflection, x equals 4. back into the original function. All right, so let me rewrite the original function again. I can't see it all on my screen, so x squared minus 1. Plus 48x squared. Was that right? Then, well, just tell me the rest because I don't remember now. Minus 64x, okay. All right, so I need f of 1. So one way to do it would be to plug it into this, add, subtract, all that good stuff. Another way to do it would be to use synthetic division and the remainder theorem. So the 1 goes on the outside. Run it through synthetic division. Oh, I was putting the answer there. That's not good. So negative 11, 37, 37. And then really it's just a matter of adding those two numbers rather than crunching the whole thing. And it works even better when you have like fractions and radicals and stuff like that, because then you really don't have to do much calculation other than addition and multiplication. All right, so of course it requires you to actually do the subtraction. Negative 27. All right, so the remainder, before it was, like in synthetic division, you usually dismiss the remainder. Here, the remainder is the solution. All right, so if I had a calculator and I grabbed this function, went to the table, at the x value of 1, it would give me negative 27. If I plugged a 1 in everywhere I saw an x, it would give me a negative 27. All right, so synthetic division is a pretty quick way of getting it. Not always the easiest way, because it's like, well, I could have done, 1, for example. You do that quickly, regardless of whatever approach you use. But when you start getting away from 1, it starts getting a little crazy. But synthetic division always keeps it kind of grounded. So I need f of 2. So negative 8. So f of 2 is equal to negative 8. It's kind of a rote, mindless way of doing it, but it gets you the solution pretty quickly. And the reason why it works is because when we're looking for zeros of a function, we're actually using the remainder theorem, because the whole point behind getting the last column to add to 0 is because we want the function to have a y value equal to 0. If the y value is equal to 0, it's on the x-axis, therefore making it an x-intercept. So that everything we did before is rooted in the remainder theorem. So this is actually the parent of that other process. All right, so pretty cool stuff, I think. So then we could actually graph, because I have coordinates. And I have the most important coordinates, but this is also very incredibly important, because 1, negative 27 is telling me that I do need to scale my y-axis, because I don't have 27 boxes in a negative direction. So my y's, I'll go by, I guess, 3s. So I need to go down 9 boxes. For x, I think I'm fine going by 1s. So I have an x-intercept at 0, 0, 1, negative 9 based on the scale. I got a 4, 0. I feel like I'm missing one. Oh, 2, negative 8. So 3, 6, it'd be like, meh. All right, so it's going to be pretty skinny, but So that's generally what your graph would look like. Crappy drawing aside. Maybe like right there.